We're going to go over some of the calculations for pump flow, efficiency, and the work or the amount of work that can be done by a hydraulic system. And we're going to put the whole thing together so that we can understand what's happening when we're operating a hydraulic system. All right, so first thing we're going to do is we're going to look at, we'll put some numbers up here and explain what each is. So pump displacement. Pump speed, so with these two pieces of information we can start to figure out flow rate. So pump displacement, we're going to use 2.5 inches cubed per revolution. So that means that the pump is designed so that when it is turning, that is the volume of oil it is going to move for every revolution. We're going to give it a pump speed, something nice and simple, 2,000 revolutions per minute, RPM. Very simple math so far. So we take that 2.5, my displacement, we multiply it by our pump speed, and gives us a output of 5,000 inches cubed per minute. Okay, we're using the minute as a time. So now I take that and I'm going to divide it by 231 inches cubed per gallon. When I do this, we're going to come up with a number of 21.645 gallons per minute. All right, you'll see how we've kept everything in line, right? We're using revolutions per minute. We get 5,000 inches cubed per minute. We divide it by the gallons, and we get 21.645 gallons per minute. Now, that is under a perfect scenario. But it does not matter what style of pump we are using, there will be a little bit of loss by oil passing maybe the end of the gear or the end of a vein, and it is left in the pump. That lowers the efficiency, right? So we're going to take this, which is one of the things, and we're going to do is we're going to build or work in how efficient that system is. So I'm going to just pick an arbitrary number of 90%, right? Which isn't great, but we're going to use it. So the efficiency rating of that pump might be 90%. What does that mean? It means that this is not my actual flow rate. It's probably going to be closer to this multiplied by my efficiency rating. So if we take this, and I'm just going to move it over, right? The key thing to remember here when you're doing this is not to multiply it by 90. That's going to give you a really wacky number. But you're going to multiply it by 0.90. So if I multiply this number by this number, we end up with 19.45 gallons per minute. And this would be closer to my actual flow rate. Now, this is again a theoretical number. The only way to actually be sure of what your flow rate is would be to install a flow meter and simply take a reading. But what we can do with that is maybe give an indication on whether my pump is getting worn out or whether it needs to be rebuilt. So we can use that number. All right? So that would be all of the steps to calculate the flow rate when you have an efficiency rating. If you do not have an efficiency rating, right? We said 90%. If you do not have an efficiency rating, you cannot make that calculation. Then you would simply leave it at 21.645 gallons per minute. But if that efficiency rating is included in the information. You must take it a step further to find out what your flow rate is. Okay, so I've listed up here some pump styles, and these are the ones we have covered in the past. We have external gear pump, internal gear pump, balanced vane pump, and we could even say unbalanced vane pump. Piston pump, all styles, bend axis, variable, anything, right? And the last one, kind of a Garroter. Those are all very common styles of pumps. Now, when we are referring to it as a pump, we also know that we take the basic form of a circle and we draw the arrow out, pointing outward. If my arrow pointing outward is empty, it now becomes an air compressor. If the arrow is filled in, it's a hydraulic pump. If we have two arrows and both arrows are pointing outward from the center of the circle, that means it is a bidirectional pump. It means that that pump can be turned in either direction and we will get flow. Now, this is all a little bit of review. But what I want to also say is that we can look at this and we can know that all of these styles of pumps can actually be used as a motor as well. It's slightly different in that when we look at a pump, and we say that we are going to attach a prime mover, and the prime mover can be either a fuel-burning gas, diesel, turbine input to drive the pump. But when we look at a hydraulic motor, and remember it's a hydraulic motor, we're not going to use one pump to create and turn another pump. All right. So we use a hydraulic motor. A hydraulic motor is going to give me some mechanical movement and be able to do some work for me. If I look at it, the difference with this is that now on my circle, the arrows do not point outward, they point inward. And same rules apply. If the arrow pointing inward is single, it can turn in one direction. It's very common though for hydraulic motors to have two arrows pointing inward, which means it is bidirectional. Means it can turn in either way. The difference with this is we are going to use a line and valves and pressure regulators and everything between this and this to connect them. And what this will do is create my shaft to rotate. Then we'll simply return the oil back to a reservoir. All right? So we're going to talk a little bit about this. I'm going to clean off the board and we'll start over again, but we're going to come back to this. The big thing to remember is that we take a prime mover to drive our hydraulic pump. The hydraulic pump then creates flow, and against the resistance of a pressure regulator in here and control of some valves, we are going to push oil under pressure into a hydraulic motor. That motor then will have the shaft rotate. So it's going to be able to do some work for me. And right, we don't necessarily have to have that on the symbol. So I've redrawn this, cleaned up the board a little bit. Just going to go over a couple of things. This is, again, is my prime mover. My prime mover is responsible for turning my pump. If the prime mover doesn't work or isn't on or isn't connected to the pump, nothing will happen. So my prime mover is going in here. I want to put some numbers in this, and it's going to relate to what we talked about a little bit earlier about efficiency. So I'm going to say that my prime mover is 10 horsepower. Nice and simple. We're going to keep that 90% that we were using earlier. So if my prime mover is turning my pump, and my pump is actually working at 90%, it means that, yes, there's going to be a little less oil head pushed down here, but effectively, I will only be able to do 9 horsepower worth of work from this, because I've lost 10% through the efficiency of the pump. Though this oil now is moving down to my motor. The motor is going to have the same problems that my pumps has, because they are often kind of the same thing. It can be, like I said earlier, they can be a Gereter or an external gear or a vane pump or whatever, but they will not work at 100%. So if we use that 90% efficiency for the motor as well, it means that although I started with 10 horsepower in my prime mover, I end up with 9 horsepower capability of doing work coming into my motor. And if that is working also at 90%, it means that I'm actually only going to be able to turn that shaft with 8.1 horsepower of work coming out of it. All right? We have lost some energy going down the line. All right? Other things can be affected. The length of this line, right, and return are also going to add to the amount of energy that I'm going to lose. But the question is, what happened to that work? We know that we cannot create or destroy energy, but convert it from one form to another. But what will happen over this, right, either in the pump or along the line, is we are going to shed off some heat. And that is where my energy goes. It is given off to the atmosphere and vented in the form of heat. All right? So what we are trying to put into the pump and what we're trying to get out of the motor is always, this is always going to be less than this. We can never get more. And I'm going to say, I guess the higher efficiencies we have on the pump and motor, the closer we can get to this, but we're never going to be more than it.